Hello, this is Dr. James Camp from Lee College in Baytown, Texas, and this is my lecture on graded and action potentials for my class and Dr. Ross's class, continuing our discussion of neurophysiology. Okay, as you remember, last time we discussed that potential exists on a continuum from minus 80, say, to about plus 30 millivolts. And resting membrane potential was about minus 70. And you recall that you had at about minus 55, there was what we call threshold potential that you had to reach to get an action potential. We had excitatory potentials that drove the potential up and inhibitory potentials that drove the potential down. These potentials are called graded potentials because they come in different sizes or grades, different strengths, depending on what kind of stimulus you get. Okay, gated sodium, which you recall is Na plus, or chloride, which is Cl minus, channels exist on the plasma membrane of the dendrite and the soma. These are called gated channels because if you look at the plasma membrane, there's a channel here, but it has a gate. Okay, and these are called chemically gated channels because what opens that gate is a receptor for a neurotransmitter. And when our little neurotransmitter fits into that receptor cup, that will open the channel. Okay. So sodium or chloride channels open on the plasma membrane. Sodium and chloride both exist on the outside of the cell membrane. So you're either going to have positive or negative ions moving into the cell. As these ions move into the cell, let's say we have a negative ion that moves into the cell, you can expect the membrane potential to change slightly because we've added more negative ions to the inside of the cell. So a positive ion causes the potential to become more positive inside the cell. So that would be one of these excitatory potentials. This moves the potential closer to threshold, therefore positive signals are stimulatory. That's another word for excitatory. Negative, Cl minus channels, on the other hand, change the potential in a negative direction and are therefore inhibitory. So a neurotransmitter that opens a sodium channel, as we showed up here, would be an inhibitory neurotransmitter, such as GABA. Each change in the potential opens channels on the neighboring bits of plasma membrane, and the new ions that we've just introduced are going to travel through the cell. They're going to diffuse along the cell membrane. And so all of that working together, the potential travels along the membrane. However, the strength of this potential fades as it moves. Okay, that's why it's a local potential as well as a graded potential. Our graded potentials sum up to threshold at the axon hillock. So here's our threshold minus 55 here. Okay, and we've got, in this case, this is called temporal summation. Temporal means time. So we have 1, 2, 3, 4, 5 local positive potentials added to this cell over time, all added at the same place. And so we get 1, 2, 3, 4, 5 excitatory or stimulatory graded potentials generated. All of these add up as they get to this little area here we call the axon hillock. So let's say we had one more, a sixth. That pushes us over the threshold here, and now we're ready to have an action potential. So once the threshold is reached, an action, I always feel like I should put an exclamation point after action. Action potential fires down the axon. Okay, summing up where we've been so far, resting membrane potential is minus 70. Graded potentials change this resting potential slightly. Action potentials, however, completely reverse the resting potential from minus to plus. Okay, so as we mentioned on the previous slide, a threshold potential of minus 55 millivolts must be reached first. Then the potential immediately spikes to plus 30 millivolts, which depolarizes the membrane. This is an all or nothing event, okay? So you're going to get that same plus 30 every time, or nothing will happen. These potentials travel fast and last until the end of the axon, actually the end of the telodendria, or till we get to the axon terminals. Okay, after each action potential is a refractory period where no new action potentials can fire. Okay, a refractory period is a time in of enforced rest. Okay, get a little off color here, but the other place we use the word refractory in physiology is to describe the fact that a man, after he has a ejaculation, cannot have another erection for some period of time, can't have another sexual episode for a certain amount of time, and that waiting period is called a refractory period. So in a way, I guess you can think that the neuron here is forced to rest between action potentials in a slightly off-color way, we could say that the neuron can't get it up again for uh, a few dozen milliseconds. Okay, so the order of events at each part of the membrane, okay, so if we have our cell membrane here, here's our axon, okay, we've got our channels. This time, our cell membrane channel is not chemically gated, it is voltage gated. It's like it has a little voltmeter here that senses what's going on inside the cell. So the first step is that threshold is reached. Okay, that threshold potential is sensed by the chemically gated, remember the voltage gated channel. Then sodium channels open, letting sodium rush into the cell, flooding the cell with positive charges, and our potential now skyrockets. So if we draw time versus millivolts, we're putting along at resting membrane potential, work our way up to threshold, and then suddenly the action potential, the sodium ions rush in, and we rapidly depolarize the cell. And once we hit plus 30, this voltage gated ion channel senses that we've hit our maximum potential, and it locks shut. Okay, so the sodium channels close. Right next to that is another voltage gated ion channel, which is going to open and let potassium out. As you know, potassium is positively charged, so as positive charges leave the cell, we're going to fall back initially to where we had started, and then we actually fall a little bit further until the cell is what we call hyperpolarized. Then there is our refractory period. Okay, this happens because these sodium channels are still locked shut while the sodium-potassium pump restores resting membrane potential during that period. So it's going to push your 3 sodium out and your 2 potassium back in. Okay. And once that refractory period is over, the axon is all cleaned up and ready to conduct another action potential. But what we didn't mention is that once we hit this action potential here, okay, when all these sodiums come in, there's an electrical effect that travels down the cell and triggers the ions. It triggers the the voltage gated sodium channels at the next part of the cell to let sodium in. And so at that next part of the cell, we start an action potential at the same time that we're repolarizing the part of the cell that started it all. And so that's how this potential propagates, is it keeps triggering the next set of ion channels, one after the other after the other. Okay, this shows you a more artistic and scientifically accurate depiction of the time scale. Okay, it takes about a millisecond for the action potential to go off, and then another millisecond to resolve, and for that refractory period to take place. Okay, so that sums up our discussion of potentials. Our last neurophysiology video is going to talk about how neurotransmission occurs.